Okay, well, it's a great pleasure for me to be here. I really appreciate the chance to do it. This is a really fun topic to talk about and discuss, and I look forward to going through it with you. Um, so the question is, why is energy storage a little bit suddenly, it feels like, become so interested to the mainstream population? And there are several reasons that are captured in this one picture. Electrification of transportation is one. Um, a rapid increase in wind and solar renewable generation onto the grid is another one, and that's where I'm really going to be focusing my attention in this talk. And somebody like Elon Musk starts talking about it, people start paying attention, especially when you announce you're going to build a factory the size of the one that he has announced and in fact begun. But to really understand why storage has become of so much interest to so many people in the electricity sector, you've really got to understand a bit about how utilities operate. And so so I can get a little bit of a sense of how deeply to go into that. I mean, how many of you consider yourselves proficient in knowing about how utilities operate? So third, quarter or third. So I'm going to spend the first few slides just orienting us in how utilities operate and why the introduction of wind and solar into the generation mix poses a challenge to utility operators. And ultimately, we'll talk a bit about how storage can help address some of those challenges. Although I would say right out of the gate, it's a really complex landscape in integrating renewables into the grid, and storage could be a very powerful part of the solution. But it is really only a part of the solution. There are many ways to introduce the kinds of grid flexibility needed to manage these new technologies that are coming online. So some of the questions I hope to address, some of them actually don't have really straightforward answers. We're working really hard to answer a couple of them, particularly the last one. But some of the things I hope to get us thinking about and discussing a little bit: why does energy storage matter? What are the key technologies that are in the ground today? How much is online today, and what's going on in the R&D space in storage? And the big question, one we spend a whole lot of time on, is how much renewable generation can you put on the grid before storage actually becomes required? It ends up being a really interesting and complex question. So why it matters, but I thought I would put right up front. I just added this a little while ago, just so you know, because I don't necessarily have a reference on every single slide, but several key sources that I used in putting together a lot of this information. The DOE EPRI Electricity Storage Handbook that was published a little bit earlier this year by our sister lab, Sandia National Labs. Electricity Storage, which is the name of a presentation by one of the GSEP sponsors, Schellenberger SBC Energy Institute, and NREL's own Renewable Electricity Future Study has a pretty extensive discussion on the role of storage in the electricity system. So you got a little bit of this background yesterday in both Amory Lovin's talk and Arun Majumdar's talk about how the grid operates. But one of the key things to know, and this is actually a pretty amazing thing when you consider the size of our system, is that there's relatively very little storage online right now. I'll say that up front. So what that means is that any given moment, supply has to exactly meet demand. So I think Arun talked a little bit about how the frequency is sort of the key metric in making sure supply meets demand. If supply is dropping below demand, the frequency will drop below that 60 hertz mark. And that's a signal to the utility operators to turn up the generators a little bit. And vice versa. If supply is outpacing demand, the frequency will rise some, and that'll be the signal to turn down the generators. Of course, much of that is automated, but the amazing thing is at any given moment, if I flip on the lights, the system turns on enough generation to make sure that those lights come on, and so it's exactly balanced at any time. And you can see here supply components and demand components are listed, but at any moment supply meets demand. And this depiction over here on the left is sort of the conventional structure of the utility system, designed around central generation, one directional power flow from the large scale central generators out to over transmission lines. So those are high voltage, hundreds of thousands of volts, to a step down substation to the 13,000 volt neighborhood, and then to the end use, which is usually buildings and industry. So this is a load curve, the demand profile for a real day in a 5-state area in the Western Interconnection. It's which 5 states doesn't really matter very much, but it has a pretty conventional shape. This happens to be a day in July. So overnight, is the low point in the demand, as is intuitive. As people get up, the demand starts going up. There's one peak usually in the middle of the day, and then another peak, which is usually the highest peak, when people get home from work. So utilities are then accustomed every day, day in and day out, to dealing with variability and uncertainty on the demand side. As you can see, the load curve changes throughout the day, so that's the variability part. And they've gotten very good at predicting what that's going to look like for the next day. But they're not 100% accurate, and so that's the uncertainty part. So it varies, and how it varies is they're good at estimating, but not perfect at it. So the day ahead every day, as Arun talked about yesterday, they build a dispatch stack based on their projection. It's pretty straightforward, really. The main considerations for projecting the demand for tomorrow are you look at the demand for today, and you look at the weather for tomorrow, and then you make your estimate. And the only time it changes is they don't use Friday for Saturday. So that's different shape, different levels of demand on the weekends. So this is a real dispatch stack. Oh, it's April. Sorry, April. This is a dispatch stack that was built day ahead to meet this demand profile. You can see it's got nuclear and coal, or the base load generators. They just run flat out. That's the way utility operators like to run them. Turns out they don't have to be run that way. They actually have more coal anyway. It has a lot more flexibility than it has been historically operated. And then combined cycle gas and hydro in the West meet the variable part and the peak. And you can see it doesn't match exactly, and that's because there are interchanges of electricity across various boundaries in the Western Interconnection, and so more was generated than was actually used on this particular day. So you've got variability, uncertainty in the load. They're used to that. They can deal with that. But now what we're doing, as you can see, and as I mentioned before, sorry about that, as I mentioned before, if the frequency gets a little off, for example, or if you've missed your load forecast, they've always had the ability to turn these generators up and down. So pretty much complete control on the generation side. But now what happens if you start adding wind and solar? So this looks very busy, but it's actually pretty straightforward. This is 2 weeks in April. And the top blue line, each one of these peaks is effectively a day, just like this. So this is 2 weeks. The blue line is the actual demand on the top. The red line is real data from a collection of wind farms in the Western Interconnection. And so one of the things about once wind and solar is in place, in a least cost dispatch scenario, which they always try to meet the demand with the least possible cost. In a least cost dispatch scenario, you always take the wind and solar, because once it's in the ground, the marginal cost to produce it is zero because there's no fuel. So what that does, the way utilities think about that, is it changes the load that they're managing the rest of the dispatchable fleet to, from the blue line to the net load, which is the green line. And that's a really different line than the blue line that they're used to operating. So, and you can see some of the regularity is gone. Still, by and large, the same kind of periodicity, but you can see the wind output doesn't follow the same rules. The wind blows when it blows, and it doesn't when it doesn't. And the utilities can't control that. And so that causes variability and uncertainty in the supply. So that's a totally different ballgame at that point. I mean, variability, uncertainty of the load, no problem. Introducing now variability and uncertainty in the generation supply, a perceived big problem. It's interesting, I say that, I say perceived because even 5-7 years ago, this was kind of freaking utilities out, but the more we've learned about how we can introduce flexibility into the system, the more and more renewables utilities have been able to accommodate without adding storage. Initially, when people started contemplating 10, 15, 20% renewables penetration, everybody thought we'd get storage right now. We've got to have storage right now. Turns out not to be the case, and that one of the reasons the answer to that last question on one of my first slides gets to be a challenge is that level of penetration at which utilities believe storage is essential keeps sliding out. The better they get at managing the rest of the fleet in a flexible manner, the more new technologies that get introduced, and some including storage, but also a smarter grid, interactive loads, and the list is getting longer and longer, the more renewables that can be accommodated without substantial deployments of storage. So I also have to show you the solar, what the solar output can do to the supply side. So this is a clear sky day in Golden, Colorado, where NREL is. So if every day was like this, you got no problem, right? You have no variability, you have no uncertainty. But every day is not like this. These are the three components of the solar incident solar radiation that we use to predict the output of solar cells. But there are clouds, and the clouds do this to the output. I mean, this is proportional to the output of the solar cell. This is a measurement of the radiation itself. But you can see the day started. This is a typical summer day around Denver and Golden. Is crystal clear in the morning, then the clouds roll off the mountains in the afternoon, and this is equivalent to your output. So a lot of variability and uncertainty in the generation if you have substantial amounts of this online. So we also think about, I've mentioned a little bit of this before, but we've done a number of studies now and a variety of approaches and a variety of footprints, different levels of wind and solar penetration. One of the common themes that keeps emerging from all of those studies is that flexibility in the system is really the key to realizing a very high renewables future on the grid. And so we'll talk a little bit about flexibility for a moment. Again, at any given time, the supply has to meet the demand. Utilities concern themselves with a number of different time frames, and we'll talk about that because that's a key to what types of storage technologies are most applicable to different problems or problems that they could solve on the grid. We talked a little bit about day-ahead scheduling, and then so this is day, and minutes to hours is load following, sort of fine-tuning the generation dispatch to match the actual load that's occurring hour to hour. And then regulation is seconds to sometimes minutes where you're maintaining the frequency. So supply side flexibility, flexible generation, I kind of hinted at that. Utilities are actually starting to move coal plants around to follow wind ramps up and down. You can do that. Coal plants can do that, as it turns out. And gas, with gas displacing more and more coal, that makes for a more flexible supply mix because gas generators typically can go up and down a lot more quickly, start up more quickly. And storage also can add a lot of flexibility to the supply side. But the interesting thing, in addition to smart loads here that I've put down in demand response, you see storage on both sides, and that's a really interesting and unique aspect to what storage can bring to the grid. It's both supply and demand. I mean, if you have, for example, you're a hot summer day, you've got a lot of storage, and demand, air conditioning demand is outpacing your ability to bring on new generators, and you have storage, it's a great asset. You can dispatch the storage and maintain system reliability and power quality. On the other hand, if you have a low demand day, say in April, when you've got a lot of wind or a lot of solar, more than you can manage, right now, you typically curtail that. You basically spill that power, and it doesn't get used, but it's clean and free once you've invested the capital. There's no marginal cost, so you hate to spill it. So if you have storage, you can spill it into storage for use later. So storage works on both sides of the balance. And a little bit about markets as well, because this will come into play a little bit later when we talk about some of the barriers to realizing more storage on the grid. Right now, there are several kinds of markets, but only in select locations that allow you to capture value from storage. Ancillary service markets, that's providing that very fast response, and then there are a number of storage technologies that have very quick, even millisecond time responses to frequency, to maintain frequency. Energy markets, so again, referring to the timeline, going out minutes to hours, even multiple hours. You can help shift solar in the day, for example, to in the middle of the day to later. And capacity markets, without going too far down the rabbit hole of what happens to electricity prices with increasing renewables penetration, but because it's cheap and utilities want to take it, that tends to have a little bit of a price suppression effect overall. And if you have built a combined cycle gas generator, for example, you've built that on a certain set of financial assumptions that you're going to sell kilowatt hours, that you're going to be called on to deliver into the dispatch stack. And if a lot of wind moves into the area, for example, and you're being called on less and less, you have no incentive to keep it running or to build more. So capacity markets are starting to emerge around the country to help ensure that we have the appropriate level of reserves on hand as renewables become more and more prominent in the grid. Okay, so getting to how storage plays then. Recalling still that there are a number of different ways to bring flexibility into the grid with existing, the way it's structured, the way the existing structure is. A number of different, you can put storage actually all over the system and get value out of it. And so I just want to step through a few here. You can interconnect it as a generator, in some storage that I'll be talking about later, such as pumped hydro or compressed air energy storage, can function essentially as another generator online. So that helps you with energy management. You can interconnect it at transmission voltages, at substations, where you can use time shifting of energy that I talked about, or you can relieve, if you locate it strategically, you can relieve congestion on the transmission system. And so that's a problem in a growing number of areas in the country, because new transmission is very difficult to get sited, as was referenced yesterday. In the distribution system, you can, again, defer infrastructure upgrades potentially with strategically placed storage. You can do energy management. And you'll notice that in a lot of these technologies, you could list the whole collection of attributes at almost any level. You can operate storage. And then for end users, there, in some cases, people are installing storage because they need very high reliability power. I mean, we have a super reliable grid already, but if there's a company that's running, say, a server farm, and they can't afford to have any outage whatsoever, there could be storage on hand in large numbers there. And small-scale end users could, and this would apply to business parks or something like that, might deploy storage not only to help gain full value of their renewables, but to maybe establish a microgrid. If the rest of the grid goes down, you can disconnect and keep your system running. So pretty much anywhere in the grid, sorry about that, and anywhere in the grid, and for a large variety of applications. And storage actually can have some benefit, even quite apart from renewables. One of the interesting things about how the grid is structured today is that you have these peaks typically during a given day and a trough. And there are a handful of days every year where utility has its largest peak, and so the entire system is built around that largest peak. Essentially, you've got to be able to still deliver power on that hottest day in July or August when the air conditioning demand is so high. But one of the consequences of that is that you've got a lot of infrastructure that perpetually operates under capacity. And that's rarely a good investment to buy something that doesn't really get used very much. So storage can help with that too. And this just shows, and this is how pumped hydro started getting built in the 60s and 70s. And I'll talk a little bit more about pumped hydro in a minute. But basically you fill the storage up with cheap electricity at night, and this is a better utilization of your generators as well, so you don't have to turn everything down at night as the load ramps down. You fill storage instead, and then you deploy it during the day, so it effectively reduces your peak and changes the shape of the load curve. I mean, the utility's ideal load curve is completely flat, right? It's you manage that very easily. But the more you can reduce the peaks and valleys, the better asset utilization you realize, and the easier the system is to manage reliably. So now I'm going to step through a number of different technologies. There are many. We don't have time to go through all of them, but so I've just picked a few examples. So don't freak out too much about trying to understand everything that's on this slide. There's a lot on it. I'll pull out different parts of it as we go along and highlight them. But I want to focus for a minute over here on the right. The x-axis here is capacity of storage, so in megawatts in this case, and then the y-axis is time. And so we have these big ovals and circles on here denoting different types of storage technology and where they operate in this spectrum. So you have everything from down here, high power supercapacitors to pumped hydro storage. So you can see all of this variety of different technologies and operating characteristics that are available, and in a variety of stages of commercialization and R&D. And I'll review that just a little bit here. This side over here, which we'll get to a little bit later in the talk, talks about benefits that can be offered to the grid at these different time scales. So just another, I guess, a way to look at another way to slice this and view different kinds of technologies. I have over here on the left the types of technologies, and so these symbols will reappear on some of the slides when I'm talking about specific technologies, mechanical, electromechanical, thermal, and so forth. And then I'm going to use this. You'll also see this bar up at the top here in other slides, and it'll be in the same place, and it'll the level of maturity will be kind of highlighted when I'm talking about that particular storage. So darker is more mature, and so you can see as an example here, pumped hydro storage, very mature, a nano material based supercapacitor, still in the research phase, as examples. So pumped hydro storage, maybe from a sort of a technologist point of view, the least sexy of all of the storage, but the most prominent. I mean, it's out there in a big way, or the biggest way of any storage anyway. So let's talk about that a little bit, about what pumped hydro is. You can see a schematic up at the top, very, very simple concept. When you have surplus generation or cheap generation, you pump the water up a hill at those times. You fill a reservoir that's up high, and then when you need power later, you spill it back down through the turbine, which typically it's a reversible turbine. When you put power to it, it pumps the water up the hill, and when the water goes back through it into the lower lake, it generates electricity. So these are really very very simple and very elegant, I think, because of that. And you can see some of the numbers up top here. There's about 142 gigawatts globally installed of pumped hydro capacity. The U.S. there's about 20 gigawatts. So that's out of the U.S. system has a capacity of about 1,150 gigawatts. So not a lot of storage on a percentage basis relative to overall capacity. There are some very big ones out there. You can see the range from 100 to 1,000 megawatts. Actually, the largest one is in Virginia, the largest one in the world. It's about 3 gigawatts. So it's a big reservoir. It's a big facility. They have a variety of discharge times, 4 to 12 hours. Their response time is very fast. They're very reliable and last a long time. And they're pretty efficient. I think most of the units that are operating today tend more toward the upper end of that. Some of them even up closer to 90. So they've been along the way retrofitted. I'm very familiar with one that I've visited, and also watched them in the control room out at XL Energy, who operates the Colorado system. It's called Cabin Creek, and it's up in the mountains outside of Denver, and it's about 300 megawatts, and it'll run for 4 hours. And they built that, actually, it was Public Service Company of Colorado at the time. They built that in the 60s just because they realized they had all this coal-fired generation that was underutilized at night, and then they were scrambling on some days to meet demand during the peak periods, and so they built it. In the 60s, they pumped cheap coal electricity up the hill at night and dispatched it back in the day. But now they very much use it. The operators are kind of funny. They sort of refer to it like a friend or something. They use it to manage the high wind penetration on the grid in Colorado. We've got a lot of wind on the eastern plains and in Colorado, and they use it every day. Basically, they're pumping it up and down depending on circumstances. So just some other cool pictures, and this is the same one from up here, and then the aerial. So some of the pros and cons. You'll see I've structured a lot of the slides in the same kind of format. Pros: it's cheap. It's among the cheapest ways to store large quantities of energy, and it's mature. It's very topographically constrained, as you might imagine. That's one of the big cons. There's only so many places where you can get a sufficient, both a sufficient elevation change and a suitable place for a large reservoir at the same spot. Um, it's not suitable for distributed generation. And relatively low energy density, and also environmental issues associated with the siting and permitting that pose challenges.
Wouldn't an additional pro be that it has a lot of flexibility and so that it can do more?
No, most definitely a pro. It's very responsive, both up and down. You can adjust it quickly. And that's why those Colorado operators really like to follow the wind with it. Yeah. They've gotten very innovative at Excel about moving their coal plants around too, though. They've become very sophisticated at managing the grid with really only Cabin Creek is the only substantial storage on the Colorado system managing. Just one second, managing. I think it's up to about 1.4 gigawatts of wind on a relatively small system. Colorado's not hugely populous, not a big demand relative to a lot of places on the East Coast or California.
What's the percentage of loss?
Yeah, it does vary, and that's one of the key parameters, an area of a lot of active research is to get that round trip efficiency up, and it's really quite high for pumped hydro, and that efficiency number that I showed is the round trip efficiency. So about 85 to even some cases 90% of the electricity that you use getting the water up the hill, you recover on the return. So a few slides about molten salt. Partial of this one, we do a lot of research in this, and molten salt storage is typically used in concentrating solar power applications. It's really the most economic near-term play for storage matched with solar that we have. Usually these are nitrate type salts. Sodium nitrate, for example, is a common one, the same stuff that your bacon is cured with. But you can see very much less deployment of this kind. Is kind of a new technology. 1.3 gigawatts globally, 281 in the US. Some of the characteristics you can see here. Also quite efficient on a round trip basis. This diagram you see here, basically you heat a working fluid in parabolic troughs in this depiction, and you drive with that heated fluid a conventional turbine. So utilities actually like this because what they see is a spinning machine. It looks just like a coal or a gas machine. So that's a positive thing. This has to be deployed typically in areas with a lot of direct normal, so very clear skies, very not much haze, not much cloud. So desert conditions. Some of the larger ones are in California. In fact, in the desert in California. Not all of them have the storage. So when you add storage, you basically you heat a salt. And store it, and when you need the power, you divert the fluid through a heat exchanger, and you use the hot salt to heat the fluid instead of the sun. And so this is used for shifting the output typically of a CSP plant from the middle of the day when it's really cranking, the sun's up, it's noon, 1 o'clock, and to the peak period for many utilities tends to be that evening hour when people start getting home. So that makes the power actually a lot more valuable. I mean, we've done some really interesting analyses around capacity value versus capacity factor. I mean, capacity factor is how much, if it's rated at 100 megawatts, some kind of generator rated at 100 megawatts, and it runs 100 megawatts for all 8,760 hours out of the year, that's 100% capacity factor. But because the wind and sun aren't always producing, then they have capacity factors much less than 100. So plant like this would have a capacity factor in the desert of in mid-20s, mid-20%, 20, 27%, something like that. But the capacity value is a measure of how your output aligns with the utility's peak. The more your output can align with the peak, the higher value the power. And so that takes us, for a CSP plant in Arizona, for example, takes us from a capacity factor of about 27% to a capacity value of about 93%. So it's really a very different way to look at the power out. And that's how this has become a near-term economically viable storage option for solar. So some of the pros and cons again. It's early commercial, but it is commercial. It's reasonably large scale. These are usually can run the generators at their rated capacity for anywhere between 4 and 8 hours. Just depends on how much salt you want to invest in, the size of the tanks, and the size of your solar field. You can scale it either direction. And I've already mentioned economic viability. A couple of the cons, definitely it's a sort of a single technology application, and that particular technology has some geographic constraints. It has to be in a very high solar area. And you at these temperatures, the salts can be difficult materials to deal with. I depicted this up here just so you know it can work with towers just as well as the troughs. In fact, it works better with towers.
How long can you store the heat this way? I mean, can you shift it through multiple days?
Yes, you can. I mean, it depends on how you design the tanks, and it's just an insulation issue, really. But some of them have been designed to shift for up to 2 days. Usually they talk about a 4 to 6 hour period. And if you, one of the nice things about this technology too is that a lot of the expense is in the power block. So you can add capacity and effectively, if you wanted to, run it 24 hours. If you build the mirror field big enough to heat tanks large enough just to keep the turbine running 24 hours. I mean, you could do that. I don't know of any plants that have been certainly conceptually designed, but not actually built. Okay, batteries, the biggest blob on the chart of blobs. Batteries are really could be the answer to many, many issues. I mean, there are a lot of different kinds of battery technologies with a lot of different operating characteristics. They really span the whole spectrum, and there's conceptually anyway no reason why it couldn't be over here. If you got cost and performance parameters where they needed to be, you could string enough of anything together and make it as big as you wanted in principle. But in practice, you know, we constrained that a little bit over here. So many applications across all time scales, as you can see. So I'm going to talk about lithium-ion batteries. I'll remind you of the maturity thing here, and that's they become much more mature because of consumer electronic applications. Just as a general technology, uses for grid scale applications are not quite as mature, but the fundamentals of the technology are similar. You can see not a lot of deployment because most of what's been built so far has been in electronics and not for power systems. So it takes a long time to get to megawatts when you're talking about phones. So some of the characteristics, very wide range of power possibilities from watts to megawatts, even gigawatts. Discharge times that are also similarly broad. Response time very fast, so that means you can call on lithium-ion storage for frequency regulation, so very high value application there. Very efficient, and lifetimes are range pretty much. And some of these applications that we're talking about, we're still learning what some of those kind of lifetime characteristics might be. So renewable energy smoothing, output shifting, T&D investment deferral as an example. So this is a picture down here of a Duke Energy wind farm where they had originally installed so-called advanced lead acid batteries. They thought that they were going to be using the batteries for smoothing of the wind output. So you can imagine if you had your power electronics and controls figured properly, instead of taking the output of the wind farm right out onto the transmission grid as it's coming off the wind machines, you could run through storage if you needed to, and have the output of the storage fill in the valleys basically, and smooth the kind of firm the capacity of the wind farm as it's referred to. Well, they actually realized that they were using it more for frequency response, and the lead acid batteries weren't holding up under that kind of very quick discharge and recharge over many, many cycles. So they swapped it out to this 30 megawatt lithium ion installation, which is just an example of the type of use that it's seen. Same situation here by a wind farm in West Virginia. These are some the configurations of lead acid batteries. The large scale ones, you can count on about in something the size of a tractor trailer, on the order of a megawatt capacity for a lithium ion battery. So you can see that deployment down here. Pros: very high efficiency, extensive experience because of portable electronics, and suitable for a very wide range of applications. So lots of promise in lithium-ion batteries. Limited life cycle, that's a little bit relative. It's not so bad compared to some battery technologies. There are some environmental and safety considerations, a lot around thermal management. And thermal management is one of the cons. They tend to heat up. But this is clearly one of the technologies getting the most press, thanks to our friend Elon Musk and Tesla. And so I've included a few additional slides about this too. This is just an example of some of the research and analysis we do at NREL. This is recently published. This is the global supply chain for all of the materials and components for building manufacturing lithium-ion batteries. And some of the keys here, I won't spend a whole lot of time on it, but the blue lines are export lines. So you can see the width is the dollar volume of the export. So you can see a lot of export coming out of China for lithium-ion batteries. A lot of imports to a variety of countries, but a lot of imports to the U.S. We do some exporting of componentry. But the interesting thing here is you see this sort of semi-transparent circle. That's the gigafactory. So you can see, I just wanted to show this not only because it's fun to highlight some of what I feel like school work we're doing, but you can see that the size of the circle here for that one factory matches the size of the China circle. So it's a big deal. I mean, he does not think small, and I think we're all going to benefit from it. So this is just went online actually a little bit earlier today. I thought I would try to see what was on there. This is an artist's conception of what it's going to look like, and here's a shot of it under construction. The intent, you can see, is covered with solar. There's a wind farm over here. The intent, I know, is for it to be net zero. And to give you an idea about the size of this thing, there are a couple of different depictions I found, and it's pretty amazing, right? I mean, here's the Dallas Cowboy football stadium, and it's only a little bit smaller than Boeing's largest factory there. And the other depiction, you can see all these famous iconic buildings here, and so it's a major undertaking. Undoubtedly going to impact the cost of lithium-ion batteries. A couple of quick slides. Let's see. I want to keep an eye on I'm supposed to end at 2:50. 250, is that right? 255?
You have some extra time because the other one's scheduled to go a little later today.
Okay, well, I'll try not to hold you guys. So a little bit about high energy supercapacitors. So these are, utilities have been using capacitors in the distribution system for some time. So they have a fair amount of experience with conventional capacitors to help just maintain power quality. Principally, it props up voltage on hot days. It provides some reactive power support. And, but there's a lot of research going on to expand their capabilities and to help manage renewables, and some really fascinating applications potentially with using nanomaterials for constructing supercapacitors. But these are purely electrical. They charge up and discharge over very short time frames. You can use them to help with frequency management. You could also with some of the designs that are coming out, use them for renewable smoothing. But these tend to be fast discharge, fast charge, fast discharge technologies. You see response times on the order of milliseconds, a fairly wide range because again, you can string them together of power capabilities, very efficient, and also very long lifetimes of some of the more conventional technologies. High efficiency, pro life cycle, many life cycles, because it's basically the buildup of and discharge of a static charge, and it's very reliable, very durable, scalable. Low energy, high power but low energy tends to be one of the biggest drawbacks. It sort of limits the different kinds of applications that you can consider with supercapacitors. Let's see, requires power conditioning. That's only a little bit of a con, and then they tend to be fairly expensive. Yes.
There's a typo in the program. You actually have to repeat.
Oh, I do. There's a typo on the front end too. I was around for a lot longer than I set up, and I just wonder why nobody would show up. Okay, so chemical storage now, and I'm going to highlight. Number on the price. I have, I think, I'm going to try to go from memory here, and then as we get toward the end, I have a backup slide with a table of a variety of prices. Unless anybody else, does anybody else know for certain? I think it's about $4,500, maybe $5,000 a kilowatt, an installed kilowatt. But we'll look on the table as we get toward the end. So hydrogen storage. I know there have been some discussions about hydrogen at the meeting already. It has a lot of potential applicability. There are a number of different ways to make it. There are different ways to store it, and there are different ways to generate electricity with it. We did set up, working with our home utility, Xcel Energy, a prototype system at NREL to demonstrate viability of the concept. We ended up sort of building our own power electronics, and we put off-the-shelf electrolyzers, and we power electrolyzers with both wind and solar to make hydrogen. So that's this part of the system schematic. We pressurize the hydrogen, store it in tanks. We store it at two different pressures. One, at the lower pressure, we either burn that hydrogen in an internal combustion engine that generated electricity and put it back out on the grid, or we use it to power fuel cells that generate electricity and back out on the grid. So we were able to demonstrate this. Oh yeah, in the high pressure one we use for fueling the hydrogen shuttle bus that we used to generate. I'm sorry.
What is it?
The pressure, let's see if I can remember, 3,000 psi on the low end, 6,500, 7,000, I think, for the fueling station. Yes. So getting up to 10,000 is a little more desirable for fueling applications. But the higher the pressure, some of the challenges grow with the equipment used pressurized and safety considerations. So this is actually in Norway. This is a real system that helps to power a village. They actually use a combination of hydrogen, and here's the storage tank. It is quite a small system. They have a flywheel. This is the base of a wind turbine here. So it's being put into practice, but still not widely deployed by any means. There, you can see this is a fuel cell bank here that's connected to the grid. But some of the pros, scalable, from distributed to very large scale systems, and very low environmental impact, because if you make the hydrogen with wind and solar, then it's very positive from a carbon perspective. If you make it from methane or fossil fuels, it's not as positive from a climate perspective. Cons, still there's a lot of research going on in these areas. The longer the list of cons, the more of a research agenda you can imagine. But low round-trip efficiency, high capital cost. There are safety considerations around the pressurized hydrogen and the flammability of hydrogen. And low energy densities at ambient conditions. I mean, it has to be pressurized. That's the case for an automobile or just general storage. But there's a lot of controversy around whether hydrogen is going to become a significant part of the energy economy, and certainly the technical potential is there. There are a lot of infrastructure issues. The big auto companies. I had sort of, I guess, gotten on a little bit of the popular bandwagon in my thinking 5 or 6 years ago when I was thinking that high interest in hydrogen fuel cell vehicles was sort of waning, until we had a visit from Toyota, and they're full steam. I rode just the other day. We have in a partnership with Mercedes-Benz, or Daimler Chrysler, I guess is the name of the company. A fuel cell powered Mercedes that is it's a car with all of the fit and finish and performance you would expect from a Mercedes, and we've been doing some testing with it. We are able to drive it around. Very nice automobile, performed very well. And so the big car companies are still seem to me unquestionably pursuing a hydrogen fueled vehicle program, and they're going to be available. So now just a few words about storage R&D. I've got a couple of depictions over here. I'll get to those in a minute. Really, it runs the full spectrum of considerations for performance and cost characteristics of any storage technology. A lot of research in novel materials, and for all aspects of, say, batteries. These are the examples I have here: anode materials, cathode materials, and electrolytes. A lot of the research that's done on those aspects of battery technology are really meant to address many on this list. A lot of work going on for higher efficiency, to get higher efficiencies out of some technologies. Not all of them are as high as like the lithium one that I showed, and in some cases approaching the high 90s. So hydrogen, that's an area where we do work in looking at fuel cells. Hydrogen has a round trip efficiency of only 35–40%. So a lot of research we do in getting that efficiency up, as you can imagine, it's one of the biggest levers on the economic viability of some of these technologies. If you're running at efficiencies that low, it really becomes difficult to make them economically viable. So higher energy densities. This is big just in general, but particularly for transportation, as you can imagine. More power per weight, per unit mass, more energy and power per volume. Lifetimes, it's another huge lever for the economic viability of storage. You've got to increase the number of cycles. You've got to be able to discharge them deeply and recharge them multiple times, and have them maintain some minimal performance characteristics. Cost always. Form factor, some very interesting stuff going on in form factor research, which is here at Stanford and other places. This picture down here I'll get to in a second. And thermal management, particularly with the lithium technologies, but many other technologies have thermal issues. Some of them, in fact, one storage technology, sodium sulfur batteries that have many appealing characteristics, have to be operated at 300 degrees C, and so it makes it really problematic for wide-scale deployment. So these are just a couple of depictions here of a flow battery. Flow batteries are one of the areas that are being invested in most heavily by DOE's ARPA-E program. They have a lot of appealing characteristics, very, very scalable, reasonably safe. You're not dealing with really high temperatures or really high pressures. And a fairly simple concept. Basically, this is just you flow one electrolyte into they have referred to here as the regenerative fuel cell, and it flows through a membrane, separates the ions, and creates a charge. And so a lot of very scalable this is. You basically scale it by the size of your tanks and the amount of fluid that you have. Getting a lot of attention by utilities. And then it's kind of at the other extreme is this happens to be a picture from Volvo, where they're using graphene sheets, so looking at single layer sheets of carbon, oriented carbon, and making supercapacitors out of that. So basically a carbon fiber panel, like Amory Lovins talked about yesterday, very lightweight panel on your car, but it also doubles as a supercapacitor that gets charged up when you brake and then discharged into your drivetrain battery. So very clever. I think we're going to see some really fascinating things happen in the transportation sector. The work that is an ARPA-E award, I think, here at Stanford is also fascinating, where there is the use of structural carbon in the chassis design that doubles also as a storage mechanism. So an enormous amount to do, and I'll get to a little bit of the importance of the R&D in a moment. Yes.
Could you say a little bit more about thermal management in lithium-ion batteries?
They heat up during the charging and discharging cycle, lithium-ion batteries, and in some cases, I mean, it's not an area that I'm an expert in by any means, but I know at NREL we have a rather large laboratory set up to do different form factors, different lithium-ion configurations, layering configurations that help to mitigate some of that in the first place. But then we do a lot of research as well in how to manage that heat once it is generated in the automobile without getting to temperatures that could actually pose a hazard, but also just the more mundane of not heating up the automobile in a way that you're taking power away from the drivetrain to the air conditioner. So I'll maybe go through these a little bit quickly, just some maps of where storage is deployed today, large-scale storage. First, I forgot about this slide, a little bit of the history, but I think I've hit on some aspects of this anyway along the way. Pumped hydro started actually well before 1980 and was getting deployed fairly rapidly initially until there was started the natural gas price drops, and the idea initially was the same concept as Xcel used when they built Cabin Creek. Use cheap power from your base load to pump water up the hill at night, and then let it back down in the day. There was the thought of doing that with nuclear plants because we were on a large scale nuclear build out at the time, but a lot changed along the way. Natural gas prices dropped quite a bit. The nuclear build-out stalled after a couple of accidents, and there were cheaper ways with natural gas being low cost. Natural gas generators were a cheaper and easier way to get some more flexibility on the grid to manage the peaks and load forecast errors. So after that valley in the 90s and early 2000s, now interest has reemerged, and I would wager to say is not going to go away anytime soon, largely driven by the rapid increase in deployment of wind and solar onto the grid. And for all those reasons I spent in those early slides of trying to manage the introduction of variability and uncertainty in the supply, storage has become more and more of a prominent issue in the electricity sector, and it's driving a lot of research. It's driving some pretty aggressive research agendas on the part of DOE and a number of universities for sure. So these actually don't show up that well. You can sort of see the U.S. Or North America here in the outline. And the color codes over here, you can see it's dominated by pumped hydro. What you really can't see very well is that there are starting to emerge these little dots. The size of the dots are proportional to the capacity of the storage. So all of these types of storage that I had on the chart, electrochemical down through thermal storage, are starting to show up on the map. But out of this total of about 21 gigawatts of large-scale storage that we have in the U.S., there is 20 of it that's pumped hydro. So we only have about a gigawatt of other kinds of storage. I think we're going to start seeing a shift in that before too much longer. Here's the global picture, again, about 148 gigawatts, but globally as well, it's dominated by pumped hydro. You can see a couple of other things that show up. These are thermal storage plants. The green is compressed air energy storage. It's an interesting technology. It's actually been, the technical viability has been demonstrated for some time. This plant in Alabama was built in the 80s, I believe. There are a couple of plants in Germany that have been built out for a long time and operating effectively ever since. Certainly some geographic constraints with that. There are issues related to having to heat the air as it's released to drive a turbine. But still dominated by pumped hydro storage. This is energy projects in the pipeline. You can see that, I mean, there are some different sources for this kind of data. I'm putting up a little bit of a conservative number here. You can find some information that would suggest there's more storage being planned than this, but about 6 gigawatts that I consider to be reasonably verifiable that are in the works, different stages of design and permitting. And diversity is starting to creep in a little bit more. There's a compressed air energy storage facility being built in Texas, another one in California, but also some more pumped hydro as well. And you can see the dots for the electrochemical installations starting to get a little bit bigger. That's lithium ion and some flow batteries. And here's a chart of the global pipeline. You can still see dominated by pumped hydro, but the electrochemical and electromechanical starting to get a little more significant in the coming 5 years. Yes, sir.
Given the siting challenges you mentioned earlier around pumped hydro,
yeah.
Is there any way, or has anyone tried to do an assessment of the total sort of possible capacity for this in relevant geographies?
Yes, and I have, for the U.S. anyway, I've seen an analysis of possible capacity, but I'm not remembering the number. But
it's a big number?
No, it's not enormous. It's not enormous. It's not going to solve all of our issues. Yes, sir.
So the negative of storage is demand response, turning down demand instead of turning up supply.
Uh-huh.
Do you know in California whether the potential for demand response is in the same order of magnitude as the potential for existing storage, or are they mismatched?
No, I think it's probably, and again, I'm not going to remember exact numbers, but experience in looking at this kind of stuff would suggest that the potential for efficiency, the reduction in demand, is much greater than what's existing in storage right now. So a few slides now about challenges and barriers. We've talked a little bit already about some of the technical hurdles that cost, performance, and so forth that some storage technologies face. So this gets to talking about some of these grid services and how you value storage. This is a huge issue for seeing large uptake of storage on the grid. These variety of different applications at these different time lines, from providing reserves and black starts at power plants and things in that days kind of time frame, all the way down to smoothing output for renewables and frequency regulation. There are not a lot of markets that allow you to capture that value. I wanted to put this in right at the front end too, just to give you a sense of how some of the costs. You can find storage ranging anywhere from $1,000 to $5,000 a kilowatt right now, commercially available storage. So a pretty wide range of prices, and you can see there are two ways that you can price storage. And this is the same way with power generation generally, is either by capacity or by the cost per energy unit out of the storage. So pumped hydro, you can see, is down in the 2,500 to 4,000 range, again depending, I'm sure, a lot on topography and the size of the plant, and a variety of different K's numbers you can see here. But all in this $1,000 to $5,000 range. Some of the advanced lead acid battery, some of the flow batteries down here. I think the published numbers for the lithium-ion batteries out of the Gigafactory are actually their current numbers for Tesla right now are around 250 a kilowatt hour. So you can compare that over here. Very aggressive.
Careful with that Tesla number. A lot of these numbers are for installed systems. That Tesla number is not for.
Is for the. So do you remember what the Powerwall cost was? So not the transportation application.
For their system, it's double what Tesla said was the battery.
So the batteries.
Installed. It's not clear that
whether or not that includes the solar.
Oh, that doesn't.
So
No.
So it's not the complete system, but it's just.
The system. There are also issues about how fast that can charge. Charge. So.
Yeah. No. There's nearly any time you can talk about a specific example. These kinds of questions can start arising.
One that breaks away from the rest of the pack.
Yeah. So moving on here to some of the ways to value storage. I mean, there are a number of different analyses where we try to determine if there is proposed storage going into the system, how might it get valued? I mean, there are places where there are markets that pay for services that storage can provide, from capacity markets to regulation markets, price arbitrage. So that's one way, and we do that. We use that as a benchmark in a lot of cases. How much are people getting paid for the services that they offer with their storage? More common way to evaluate storage, because there aren't that many markets that allow you to get paid, are on avoided costs. So A great example is a couple of different examples is that avoided infrastructure upgrades. If you can do that, if you can keep from digging up and burying 2 or 3 miles of distribution feeder by adding some storage, you can defer that investment to a later time potentially. Also, when you add any kind of generator, this was an interesting comment in the plenary yesterday, when you add any kind of generator, including wind or solar, there's an integration cost to that, and that cost is usually driven by the need to add reserves. There are FERC and NERC requirements, regulatory requirements to maintain a certain amount of reserve. So if I add a really large plant onto my system, 1,000 gigawatts, I've got to have, by regulation, a certain amount of reserve to back that thing up. So there's a cost to any kind of generation, and so you can storage can help you defer some of that in addition to providing many of these other benefits. So it's very flexible kind of asset to have in your system. So, and then we can look at it and compare it to competing technologies and somebody's willingness to pay for competing technologies. I mean, the reserve example is a good one for that. So using more of the cheapest of pump hydro and some other the cheaper, so being very generous, I guess I should say, in the life cycle in the installed cost. If I draw the line at $2,000 a kilowatt, that's at the low end. If you do a search of the literature, you see a range of values assigned to storage for different applications. And the message of the slide is really only frequency regulation right now has a life cycle value for storage that is that's greater than the cost to install. So this is a huge challenge. I think that the emergence of markets that actually the very important thing about this slide is that each of these value streams, so a capacity value, for example, or a regulation value, contingency reserve value, these are considered in isolation. But the reality is many storage technologies would allow you to play in multiple markets. So if those markets exist, it's going to make a big difference in the ability to invest in and earn a return on storage technologies. Market and regulatory challenges, I've already hit on a number of these. Storage isn't always eligible to participate. In many cases, in regulated utilities, there are no ancillary service markets to start with, so utilities have to consider this kind of how they're going to maintain frequency regulation in by considering a suite of technologies and then picking the one that's going to offer them the performance that they need at the lowest cost. So that's how storage gets evaluated. This is a really interesting one, the second bullet, ownership of storage plants. In unbundled systems, a lot of times transmission and distribution system operators are not allowed to own generation assets, and in many of those same places, storage, even though it can be either a supply side or a demand side asset, are considered a supply side asset. So they're not even allowed to own storage even if they wanted to. So, and they're also, I mean, this is actually a much longer list than this one slide, but to monetize the rapidness of the response, very critical thing to utilities to be able to maintain frequency. A lot of regulations around that, as you could imagine, and to have fast response technologies is important, but it's not valued in any markets.
They have to, all of the ISOs have to figure out how to pay value factors.
So that they're
PJMs are included in the market.
The PJM's market is in, so there are some markets in the East. I know the ISO, New York ISO, also has, has this, has the frequency or the regulation market for sure. But in the West, only California has this operating systems operator. So the rest of the West is not market-based like California or PJM or New York ISO. So just a slide in case there are people here who are unfamiliar with this. I put this in sort of the market and policy section because this is one type of policy lever that can really drive a lot of technology change. A mandate to include the equivalent of all non-pumped hydro storage that's in the ground in the U.S. right now by 2020, so 1.3 gigawatts. As you remember, we've got about 20 gigawatts of pumped hydro and another gigawatt of everything else. So not pumped hydro, my understanding, is excluded. And they specify what parts of the system different amounts have to go in. So it's a very interesting rule. And some of the objectives that were stated are many of the things that we've been talking about already. Optimization of the grid, including peak reduction, contribution to reliability, deferment of transmission and distribution upgrade investments. So these are the thinking of the PUC when this was developed. Integration of renewables and reduction, subsequent reduction of greenhouse gases. Yes.
Was that something that's been passed or has been intended or what?
Yes.
It's important.
Yeah.
A year ago.
So this is just summarizes really where storage is valued in electricity markets today. You can see the key up at the top. Green circle is yes, partially or indirectly is a yellow, and the orange is no. And you can, instead of me going through this one, this is perhaps a good one to look at given the time, because these will all be posted, of course. You can go back and look later. But you can see that there are areas where there is frequency regulation is a green there in the ISO in many of the markets in the East, and with the FERC rule increasing. So I'm going to wrap up with kind of the big question is how much renewables can you get on the grid without having to have storage? And the most unsatisfying answer is that it depends. It depends on a lot of different things. What kind of footprint you're talking about, what your current generation mix is, how good your renewable resource forecasts are. There are many variables, and a lot of these things are shifting as we introduce new technology into the marketplace. So they're learning. A lot of utilities are learning really well, learning really quickly as they go. Honestly, it was probably just 5 or 7 years ago when we would engage with utilities and kind of at the front end of some of our first large-scale sort of interconnection-wide integration studies. And some utilities would get nervous if you started talking about 5% penetration, and 10% was conventional wisdom at the time. 10% was really kind of the top end. You know, there's no way 10%, if we go over that, we're going to have more storage. Now 20% is very commonly and rationally discussed, and without anybody panicking. And there are examples of systems in Europe and even the Colorado system on a sort of an instantaneous, and by instantaneous I'm talking in utility terms, which is an hour. Instantaneous penetrations in Colorado have gotten up close to 60% on occasion of wind penetration. Overnight, one of the struggles actually with the wind belt, the central plains in the U.S., the wind tends to blow more overnight when there's no demand. There have been a few occasions. I think the most recent, the peak for the Colorado system was just in the spring, where overnight, low demand, I think it was March, low demand, very high wind penetration. So for an hour, Excel kept all the lights on at an effective 60% penetration of wind energy in the Colorado system. And you see that those kind of numbers happening more and more in Europe. And so they have learned along the way. I mean, fortunately, they didn't have to go from no wind to 1.5 gigawatts of wind. They've learned how to manage their system as they've gone and have not added any storage, any substantial storage. They have Cabin Creek, but that's about it. So this is a qualitative slide, I'll hasten to add, but this is one of the ways we think about it. I come back to one of the initial slides. The key really is flexibility, and whatever way you can bring flexibility to your system is going to allow you to incorporate more renewables without having to invest in storage. So the x-axis here in this conceptual representation is increasing penetration. And the y-axis is cost from low to high. And we've depicted here different types of supply side and demand side flexibility and at what point you might want to think about deploying them based on current cost and current grid operating conditions. And you can see here that on the supply side, the cheapest thing to do, the first thing you should do, is to make the most out of the flexibility of your existing fleet. As I pointed out earlier, coal even turns out, you can ramp coal actually a lot. I've seen some of the figures from Excel where they've had wind ramps that amounted to about 800 megawatts in an hour. So one of their the size of one of their largest coal plants ramping down in an hour and ramping back up at the same rate. They've learned to move their coal plants around. Doesn't come without a cost, but they can technically do it.
I've seen some parts that approach only steel, probably used in large steel plants. When you do that thermally, it's like it fertilizes it.
It does.
Which causes the operating costs to go up. And once they start going up into the sea dive, you basically already crashed the plant. I've heard stories of 20-year lifetime plants being used for 2 years.
So I haven't heard this story quite that dramatic. I'd be interested in learning more about it. But we've done a series of high penetration by high, in this case, I mean 35% wind and solar in the Western interconnection. We've done a series of 3 studies about the impact of that level of penetration in the Western interconnection. The first one was an operational study. Can you operate it? The second one was addressing exactly this. It was just a huge unknown. We knew that cycling plants was going to cause this kind of thermal stress that they were not designed necessarily for, but we wanted to quantify that. So we worked very closely with a number of different folks, including utilities, coal plant operators, and in the end determined that that increase in the O&M cost to be on the order of about $5 a megawatt hour. So about 0.5 cents a kilowatt hour is what it's actually a little bit of a range, but that's a number that you can go to. I haven't heard of actually plants, the overall lifetime of a plant being reduced by that kind of dramatic number that you talk about, but I'd be interested in learning some more about that. So we have tried to quantify that. Another report about the time the first Western wind and solar study came out suggested that carbon emissions from coal and gas plants actually went up because you tended to operate them off their design point. So they were operating less efficiently. So we wanted to quantify that too, and we did that in the second study, along with looking at the thermal fatigue issues in coal plants, and learned that actually the emissions per megawatt hour from a coal plant do go up, but the offset in coal and gas generation from that much wind and solar far overwhelms that slight increase in per unit energy emissions.
The day after the study on that, where you saw big emissions increases, did
Uh, No, the study that we worked with the most in Excel was involved quite a bit because it was talking specifically about the Colorado system. Was a study by a group by Bentech. They subsequently have retracted that paper. So, and then looking quickly at the demand side, markets is and that's actually the case. That should be up here in the supply side too. There are a lot of things that can be done with electricity markets that encourage more rapid dispatch, and because wind and solar don't change only on the hour, they change all inter hour. If you can dispatch and you have market structures that allow you to buy and sell inter hour, you can follow the wind and solar a lot more closely and reduce the reserves that you have to have online as a result. But one of the things that you see here, and this is really the biggest barrier to storage today, is that electricity storage is still one of the most expensive things that you can add to your system to gain flexibility. Now, I think, and some of our research shows that storage will unquestionably be an important part of the solution when you start getting to really high penetrations of wind and solar. And that's why the research now is so critical. You can't wait till you need it, right, to start trying to figure it out. So that's why you see all these pilot projects, these demonstrations. You see a heavy investment by the Department of Energy in through ARPA-E and in new technologies and addressing those cost and performance parameters that I listed up there. I also just added this just a little bit earlier, just to talk about other sources of flexibility that aren't depicted on here. One of the best things that you can do is improve your wind and solar forecast. And there are companies that have emerged that provide utility operators with this kind of data that show them not how much wind is going to blow or how much the sun is going to shine, but what power output they can expect from their plants, from their fleet, and at what times of day, so they can manage the dispatchable fleet around that. You can imagine that's a very important thing to get right. Expanded transmission networks also add a lot to the flexibility of the system, but that's a hard thing to get accomplished. Smarter distribution system and smarter load. I mean, this is, to me, one of the great intriguing areas for the grid in the future is what's going to be happening on the distribution system. Technologies are coming online so quickly that will allow, I mean, buildings have been built to just basically take power, but the technology is emerging now that will allow buildings to be fully interactive participants in the grid. And the market structures have to be there. They're not there now. But you could imagine a grid that's much more flexible, accommodating a much wider variety of technologies, and operating with high power quality and high reliability. I mean, you can see that future with the technologies that are coming on, and maybe part two of this can be the impact of electrification of transportation and all of that having all of those cars plugged into the system could offer, with the right kinds of controls, the right kind of market signals, and the right. Am I getting, is that 5 minutes or okay?
Quick two-part question.
Yes.
There's the box, middle upper box, renewable energy curtailment.
Yes.
So you shut down the sun or shut down the wind?
No, you turn off the inverter or you feather the blades on the wind. You can turn them down.
Is it a positive thing to do?
In some cases, it's the most economic thing to do.
Because of shutting down the sun.
Yeah, if you have very high penetration, for example, you're required to keep a certain amount of spinning reserves online, and you can't turn them down anymore. Then to maintain the requirements.
How is regulation out of sync with technology? Adoption and slowing down?
That's an entirely another tutorial. No, it's it's a very dynamic environment, both in the technology side and the regulatory side. There's a lot of things coming online as there are a number of FERC rules now that are beginning to address new technologies coming online. One was referenced earlier. We had a little bit of an impact, I'd like to think, in something called energy imbalance markets that have been introduced in the West, and that allows balancing areas to share power where they inter-hour, where they didn't used to be able to do that. So expanding the geography of the area where supply has to meet demand offers a lot more flexibility. And no, it's yes, it's out of step, I can tell you. So I'm going to wind up now with just a couple of slides from our Renewable Energy Future study. What we did is examined a number of different cases of penetration levels of renewable generators, and all the generators that we modeled are over here on the right. So it's everything, storage down through coal and nuclear. And for this chart, I wanted to show you the main thing is that the top gray slice of the bar is storage. And you can see that when we modeled this system, and we modeled it using a capacity expansion model that we developed at NREL, that based on the input constraints, I want this much wind or this much solar, it goes and seeks out the best sites. It figuratively builds those plants out until you reach that level of penetration. And it builds the transmission out that's necessary to connect all of that generation up. And so we built out this system at all these different levels and determined using an hourly operating model, utility operating model, that you could actually operate this system. But the interesting thing is you see storage grows considerably. It grows up from the 20 gigawatts we have to about 150 additional gigawatts. And we focused mostly on this 80% scenario. So that's a lot of additional storage, but it's not as much as many people thought it might be in the early days of considering renewable penetration. So, and then I will end with this, what I feel like is a really cool visual of, this is, in the model, we built out this system out to 2050. With 80% renewables. So renewables include geothermal, direct fire biomass, solar, both distributed and utility scale, and wind, utility scale. And then we populated that system into a model called Plexos, which is a sub-hourly utility operations model that shows how your generation assets can meet an assumed load. So we built the system out to 2050. We put 80% renewables in it, and then we ran for an entire year the operations model, hour by hour. And one of our conclusions in this case is that you can keep the lights on if you do that. So that's a big number, 80%. And this is just kind of a fun little visualization. When the power plants are operating, the colors get larger and they come and fade. And this is a couple of week period in July that's being, you can see the date moving down here, July and August, that's being modeled. You can see the sun coming up here in the west and the wind picking up in the plains. So storage is, as I said, I think storage will undoubtedly be a major part of the future system, but when it's required is going to be very variable depending on circumstances, depending on region, depending on other generation assets and what you're trying to achieve, and markets and regulation. So I really appreciate everybody's attention. I'm happy to answer more questions if you have them.